So now that we've discussed the fate of irradiation on a surface, and we've said that it could be reflected, absorbed, or transmitted, now I want to introduce to you three more radiation properties of a surface. They're called reflectivity, absorptivity, and transmissivity. We use rho, alpha, and tau for the symbols, and we define them as the fraction of irradiation that is reflected. We call that one reflectivity. Fraction of irradiation that's absorbed, we call it absorptivity, and fraction of irradiation that is transmitted through the medium, we call that transmissivity. If I want to actually see what the relation between these three is, I would look at the relation that I've seen before. I said that the total irradiation on a surface, G, is equal to the sum of irradiation that's going to be transmitted, irradiation that's going to be absorbed, and irradiation that's going to be reflected. If I divide all the terms by G, then I'll be able to, on the right hand side, I'll have G over G, which becomes equal to 1. And then I'll have the fractions, actually. I'll have G of reflection over the total G, and then I'll have G of absorption over the total G, and then I have G transmitted over the total G. Or in other words, the fraction of radiation that's reflected plus the fraction of radiation that's absorbed plus the fraction of irradiation that is transmitted is going to be equal to 1. So then I'll have rho plus alpha plus tau, which are going to be equal to 1. This is for any medium in general. And then for an opaque medium, we said that we can't have any of the irradiation transmitted through the surface or through the body. And in those cases, the tau is not going to be there. There's not going to be any fraction of irradiation that's going to be transmitted through the body. And in those cases, we'll have rho plus alpha is equal to 1. In other words, if you do have, for example, for any medium, if you have rho plus alpha plus tau equals to 1, if you have two of these properties, you can define the third one, for example. Or in an opaque surface, if I know what my absorptivity is, I can define what my reflectivity is, because whatever is not absorbed is going to be reflected. So in this slide, a summary of radiation heat fluxes is given to you. I'm going to quickly go over some of these. We have seen all of these before. So the first is emissive power, which we show by E, and this is the rate at which radiation is emitted from a surface per unit area. This is the result of your surface being at a temperature that is higher than absolute zero. And depending on the emissivity of your surface, you will get different emissive powers. So on the very right column, you see that you have emissivity multiplied by Stefan-Boltzmann constant and temperature to the power of 4. The Stefan-Boltzmann constant and temperature to the power of 4, this part is the emission or emissive power of a black body. But of course, the surface that you're talking about is not a black body. It has its own emissivity, and that's why you do have to multiply it by emissivity to get your emissive power of your specific surface. Then there's irradiation, which is the rate at which radiation is incident upon a surface per unit area. This is radiation incident upon a surface, and we don't know what may happen to it depending on different surfaces. Some of it may get reflected, some of it may transmit through the surface, and some of it may get absorbed. In the case of opaque surfaces, none of it will get transmitted through the surface, and it will either be reflected or absorbed on the surface. And then there's radiosity. We talked about this in the last lecture as well. It's the rate at which radiation leaves a surface per unit area. So this could be radiation that's from reflection of irradiation on the surface, or it could be radiation because of emission from the surface itself. The difference between reflection of the radiation or the emission from the surface is irradiation incident upon a surface. Reflected part of it, it doesn't generally impact the surface or the body of the surface belongs to itself. It doesn't affect that. It's basically reflecting what comes to the surface, whereas emission comes from the energy content of the body itself because of its temperature. So as you have more and more emission, if you have no way to provide more energy to the body, your body will start cooling down as a result of emission. So you will notice here that you have emission that could come off of the body, or you could have rho G. G would be the total irradiation incident on a body, and then rho multiplied by G would be the fraction of irradiation that's actually being reflected. And then the last one is net radiative flux, which we call net rate of radiation leaving a surface per unit area. So this is your radiosity, whatever comes out of the surface, minus the irradiation part of it, minus what doesn't really come from the body itself, but what came just through irradiation. So this is what we call net radiative heat flux. And for the case of opaque surfaces, your irradiation was given to you in the third row, so you could write your radiation as E plus rho G, which I'll write like this. So for the opaque surface, I'll say it would be E plus rho G. I'm using this relation. So that's for my J, and then I'll say minus the J, minus the G, irradiation, minus irradiation. And I know my irradiation is actually two components for a opaque surface. My irradiation is a combination of my absorbed irradiation and reflected irradiation. So if you actually cancel this rho G with this rho G, you will be able to get the relation that you see here. Or in other words, your E, your emissive power, is actually your epsilon Stefan-Boltzmann constant T to the power 4. So this will become Stefan-Boltzmann constant T to the power 4 epsilon, and then you will have minus alpha G. That's how we would get a relation like this. So now we're going back to the definition of absorptivity, reflectivity, and transmissivity. We said that these are basically related to the fate of irradiation on the surface, incident on the surface. Some of it is going to be absorbed, reflected, or transmitted. We defined them as total, for example, hemispherical absorptivity. We defined it as the fraction of irradiation that is going to be absorbed by the surface. Reflectivity was the fraction that was going to be reflected by the surface. You can see that there is a ratio here, G reflected divided by G, which is the total irradiation on the surface. And then the transmissivity was the fraction of transmitted irradiation, the irradiation that is going to be transmitted through this body divided by the total irradiation. Now, the same discussion that we had around emissivity, and we said that it's a property of the surface, but it's also not going to be constant. It's going to be dependent on, for example, direction and the wavelength. We can say the same thing for absorptivity and reflectivity. They are functions of the direction and the wavelength that you're looking at. So, for example, at a given wavelength, your absorptivity may be different than another wavelength. At a different direction, it could be different. So, in general, we do have more advanced relations in order to calculate these. For the sake of simplicity, in many of the examples that we deal with in this course, we are going to consider them over all the different wavelengths and over all the different directions. Kind of an average calculation is used here. But in general, we know that specifically in different wavelengths and in different directions, you are going to have different absorptivity. It is a function of direction and the wavelength. Here, one more note on reflectivity is given to you here. As I said, reflectivity does depend on the direction. For example, here you have incident radiation, let's say to a point in a surface, what's coming in from whatever other surface. What could happen to it is it could have reflection in all reflection similar in all directions. So the radiation intensity or reflected radiation intensity would be uniform in the left picture here. So you can see that we have uniform reflection of that incident ray. But then you could have the incident ray and then it could actually come off exactly like a reflected ray like this. So this one, the right-hand side one, is not actually diffuse. This one is what we call specular reflection, whereas the left-hand side one is what we call diffuse reflection. So you could have these types of variations as well, which you have to be careful how to do your analysis. As I mentioned, reflectivity and absorptivity and also transmissivity, they all depend on your wavelength. Here in this graph, we're talking about opaque materials. And on the left vertical axis, you have reflectivity, and on the right-hand side, you have absorptivity. So basically, at any, if you look at any of these lines, you will be able to see that for whatever wavelength in the horizontal line, you can look at a certain line, which is basically like human skin, snow, white paint, different types of surfaces. You can take a look at them and see what their reflectivity is and what their absorptivity is. You can see that on the different regions of the wavelengths, the same material may have different amounts of absorptivity or reflectivity, and that's what we were talking about before as well. When we talk about a certain type of surface and its reflectivity and absorptivity, it's often important for us to know exactly at what wavelength we're talking about. Same material that could be very reflective for a given wavelength may not be so reflective for another wavelength. Now here you see the same typical same graph as we saw before, but this one is for spectral transmissivity. Again, we call it spectral transmissivity because we're now showing transmissivity as a function of wavelength on the horizontal axis. This is for semi-transparent materials. As we said before, opaque materials are not, their transmissivity is basically zero. No fraction of incident radiation transmits through the surface and goes into the body, or transmits through the body of the material. So now here, for example, you see for glass, we have low iron glass and we have high iron glass. You can see that the transmissivity of glass depends on the amount of iron that's used in its making. We also notice that in the infrared region, which is the higher wavelengths, Tedlar, which is a kind of plastic, is actually has higher transmissivity than, for example, glass. These types of information become important when we're talking about design of, let's say, solar collectors. That cover, the top cover of solar collectors, what should that be made of? In order for the solar radiation to transmit through the whatever cover that we select. These types of information will help us in designing different types of material for different types of radiation problems. We have seen before that a surface property like emissivity is not only a function of wavelength and direction, but it also is a function of the temperature of the surface. Now we want to look at absorptivity. That is also a property of the surface, and we want to see how it changes with temperature. We do find that the absorptivity of a surface is not, it is a function of temperature, but not a function of the temperature of the surface itself. It's a function of the temperature of the source that is generating the radiation. So for example, the roof of your house could receive radiation from the sun at a very high temperature, and it also could receive radiation from the surrounding buildings and trees at lower temperature. The radiation that's coming from the buildings and trees at lower temperature would result in absorptivity of your surface, your roof surface, to be at 0.9, and the solar radiation coming from the sun at a higher temperature would result in your surface absorptivity of 0.6. So we basically say that the absorptivity of your surface depends on the temperature of the source, not the temperature of itself. This is the opposite of the case with emissivity. Now let's take a look at this graph here. You have the absorptivity as a function of temperature, but not the temperature of the surface itself, the temperature of the source of radiation. And different types of, for example, different types of surfaces are listed here. Of course, surfaces are different, but then if the temperature of the source changes, some of them, you'll see that there is an increase in the absorptivity, and in some of them, as the temperature of the source changes, for example, it goes up, the absorptivity could actually go down. We generally, when we do the comparison, we notice that the absorptivity increases with the source temperature for metals. So for example, a piece of metal absorbs most of solar radiation because it is coming from a very high temperature source like the sun, but it absorbs less of, let's say, surrounding objects at room temperature. This is for the case of metals, but for the case of electric non-conductors, it's actually the opposite. Electric non-conductors, like the roof of your house, the higher the temperature of the source of radiation, the lower the absorptivity becomes. That is why, for the example here, for the roof of your house, because it's an electric non-conductor, it is actually absorbing more of the irradiation from the same temperature trees and buildings outside than it is getting absorbing the radiation from the sun, which is at higher temperature.